So, good evening, everyone. Let us continue our discussion for the second week. So, in this week, we'll be basically studying about the condition evaluation and testing. So, this lecture basically will be dedicating to identifying the distresses. So, the concepts covered will be types of evaluation, identification of distresses in concrete structures. And if we see here, there are various types of evaluation such as visual inspection, semi-destructive testing, non-destructive testing, and structural health monitoring. So, in case of visual inspection, basically it is used to recognize the type of serviceability defects, to identify any signs of material deterioration, to identify any signs of structural distress and deformation, and to identify any addition, alteration, misuse in structure which may be causing the overload. The visual inspection basically it provides the general information of the structure. The identification of distresses on the structural system can be for both substructure and superstructure. So in substructure, we talk about the settlement of columns, walls, floors, deflections, cracks. In superstructure, we talk about the materials, framing system, cracks, deflections, honeycombing, spalling, slenderness, rusting of exposed steel, and identification of distresses due to dampness and leakage. In the case of semi-destructive and non-destructive testing, so they can be equipment-based evaluation technique. There can be external evaluation. Then there is one-time evaluation. Then condition evaluation by the analysis of test results and estimation of quality, strength, extent of corrosion, carbonation, etc. In terms of structural health monitoring, it can be like sensor based evaluation technique, sensors attached or embedded within the structure, continuous monitoring of deflection, vibration, strain, etc., and condition evaluation by analyzing the real time responses obtained from sensors. So, the basic symptoms of distresses can be cracking, grazing, spalling, disintegration, scaling, dusting, pop out, honeycombing, buckling, seepage, delamination, corrosion, erosion, which are abrasion and cavitation. So basically, crazing in concrete is a pattern of fine, shallow cracks that appear on the concrete surface. Spalling is a localized surface breakdown. Scaling is a thin layer flakes peeling off from the surface, and delamination is a deeper layer separation within the concrete. These are various types of cracks basically which happen due to various reasons before hardening and after hardening. So before hardening it can be in form of early movement, plastic, early freezing, and in after hardening stage it can be in terms of physical, thermal, chemical, and structural. So early movement can be in the form of form movement, subgrade movement, late jointing. Plastic can be in terms of shrinkage and settlement. In terms of after hardening, the physical can be in terms of alkali aggregate reaction, drying shrinkage, restrained shrinkage, freeze thaw. Thermal can both be seasonal temperature changes and temperature gradient. In seasonal temperature changes, it can be expansion, contraction, whereas in temperature gradient, it can be curling or contraction. Chemical, it can be sulfate attack, corrosion of steel, carbonation, acid attack. So in structural, it can be overload, accident, earthquake, excessive movement, improper design, fatigue, and creep. So the types of cracks can be structural crack and non-structural crack, active crack and dormant crack, and isolated crack and pattern crack. So structural crack, it basically results from incorrect design, overloading, foundation settlement, faulty construction practices, earthquake, etc. These cracks can be horizontal, vertical, diagonal, or may even appear like a staircase, as can be seen here. So structural cracks may appear in the slabs, beams, columns, joints, or in foundation. It often extends to the upper floors of the buildings. Structural cracks may endanger the safety of a building and their components. So these are some of the examples which are shown by pictures. So this is the flexural crack on a beam tested in laboratory. These are the shear cracks, which are basically diagonal cracks on a longitudinal girder. So girder is a beam which is having a high cross-sectional area. Okay, and yeah, This is an example of shear crack on a slab tested in laboratory. So this is basically a slab. Okay, and these are the examples of diagonal cracks. Again, in a flexural member, an inclined crack caused by shear stress, usually at approximately 45 degrees to the axis. And these are the flexural cracks on a longitudinal girder. So the structural cracks can also occur in pavements. So for example, these are the transverse cracks. So transverse is along the cross section. So these are the transverse crack in concrete pavement. So transverse crack in concrete pavement due to change in temperature. Then there is corner crack in concrete pavement, and there is longitudinal crack due to large joint spacing. Okay, so these are the examples. And apart from that, there are non-structural cracks as can be shown in this schematic diagram. So these are various non-structural cracks in concrete structure. So they can be like plastic settlement, A, B, and C, plastic shrinkage, which are shown in D, E, and F. Then there is early thermal contract, shown in G and H here. So there is long-term drying shrinkage, shown in I. Then there is grazing, shown in J and K. And then there is corrosion of reinforcement, shown in L and M. And then there is alkali silica reaction, shown in N. So here, so grazing is basically, it is a pattern of fine shallow cracks that appear on the surface of concrete. And here, if you see here, cracks at the kicker joints. So kicker joint is basically a small upstream cast as part of a concrete base to allow the securing of wall shutters. So it is basically lifted. Okay, so any concrete, okay, any structure, any wall which is basically lifted from the base. So thereafter, there are active and dormant cracks. So active cracks in concrete are live cracks which expand in length, width, and depth over time. These cracks are formed due to overloading and thermal expansion, weathering effects like freeze thaw. Dormant cracks are those cracks in concrete which once occurred does not propagate or extend anymore and becomes dormant. Example, shrinkage cracks. Then there is isolated crack. So they are basically of three types. One is fine crack, which is having a size less than 1 millimeter. Then there is medium crack, which is between 1 to 2 millimeter. And then there is wide crack, which is greater than 2 millimeter. So these are cracks of varying widths, as you can see here, and also here it is an example of isolated crack. Then there is pattern crack. Okay, so pattern crack basically, so cracking in the form of a repeated sequence, and it is resulting from a decrease in volume of the material near the surface or an increase in volume of the material below the surface, or both. So they can be, the examples can be craze cracks, D cracks, diagonal cracks, hairline cracks, longitudinal cracks, transverse cracks, corner cracks, map cracking, plastic shrinkage cracking, random cracks, etc. So here it is shown the map cracking on a concrete wall. So distresses in concrete, so you can, as you can see here, so this is crazing, that is fine random cracks or fissures on a surface of concrete, cement paste, mortar, or plaster. Then there is decracking in a concrete pavement, so a series of cracks in concrete near and roughly parallel to joints and edges. So they are basically decracks. Then there is plastic shrinkage cracks, so cracking that occurs in the surface of fresh concrete soon after it is placed and while it is still plastic. Then there is spalling, as you can see here. So from the top, some chunks of concrete have been peeled off, removed. Then there is, as you can see, a fragment usually in the shape of a flake. Okay, so detached from a concrete member. So flake is basically a small thin piece of concrete surface that is peeling or chipping away. Okay. So then there is cracking and spalling, as you can see here. So this is cracking and this is spalling, and there is surface in disintegration. So reduction into small fragments and subsequently into particles. Then there is concrete dusting. So that is the development of a powdered material at the surface of hardened concrete. And then there is honeycombing. So honeycombing is voids left in concrete due to failure of the mortar to effectively fill the spaces among coarse aggregate particles. Okay. Then there is blistering. So this is basically irregular raising of a thin layer at the surface of mortar or concrete during or soon after completion of the finishing operation, bulging of the finish plaster coat. Then there is peeling. So this is a process in which thin flakes of mortar are broken away from a concrete surface. Then there is scaling. So that is basically local flaking. Okay, thin pieces of concrete are peeling away, or peeling away of the near surface portion of hardened concrete or mortar. Then there is pop out. So that is basically breaking away of small portions of a concrete surface due to localized internal pressure that leaves a shallow, typical conical depression with a broken coarse aggregate at the bottom. Then there is delamination of concrete due to corrosion in reinforcement. So that is a separation along a plane parallel to a surface or parallel to reinforcement. So basically, these terms are almost quite similar, okay? Like quite almost related, okay? Delamination, then spalling, cracking, etc. Crazing, but there are very minute differences actually. So as separation along a plane parallel to a surface or parallel to reinforcement is delamination. Then there is seepage. So seepage is due to leakage of water. So basically in this lecture, we studied about the types of evaluation, identification of distresses in concrete structures. So let us start the next lecture. So that is basically about semi-destructive testing. So here we will be basically covering pull-out test, penetration resistance test, pull-off test, and core sampling and testing. So basically semi-destructive tests, if we talk about, they are equipment-based testing. They are intended to assess in situ concrete strength but cause some localized damage also. That's why it is semi-destructive. And the damage is sufficiently small to cause no loss in structural performance. So it is not destructive test, and it is also not non-destructive test. It is semi-destructive. So the first semi-destructive test we will talk is about pull-out test. So it is basically used to estimate the in situ compressive strength of concrete. It is used for during construction to estimate the in-place strength of concrete in deciding several critical activities like formwork removal, application of post-tensioning, etc. Can take place or not. It measures the force needed to extract an embedded metal insert from a concrete mass. The ultimate pull-out force is directly correlated with the compressive strength of concrete. So the apparatus basically, so this is the schematic view of the pull-out test. So a pull-out metal insert into, this is a pull-out metal, okay. So it is insert with enlarged head, as you can see here, a bearing ring here, loading system and a load measuring system. So they are not shown here. So this is the pull-out bar basically. And these are the concrete, this is the concrete surface. So bearing ring refers to the circular metal ring, so it is circular, okay. So they basically refer to the metal ring circular that provides a stable surface against which the pull-out force is applied, ensuring that the load is distributed evenly on the concrete. So the procedure is such that initially pre-embedded insert is pulled out by a loading ram seated on a bearing ring concentric with the insert shaft. The bearing ring transmits the reaction force to the concrete. As the insert is pulled out with a force F, a conical shaped fragment of concrete is extracted from the concrete mass. Frustum geometry is controlled by the inner diameter of bearing ring, capital D, diameter of insert head, small d, and a embedment depth, small h. So if we go as per the ASTM C987 standard, so that 2 alpha, that is the apex angle. So apex angle is basically the angle at the tip of the cross cone shaped failure zone that forms when a pull-out force is applied. So basically we are talking about this angle, okay. So here, so this imaginary point, okay. So at that point, what is the angle created by these two lines? So that is basically the apex angle, and it will be equal to 2 alpha, okay. Alpha plus alpha. This 2 alpha of the idealized frustum is calculated to determine the frustum area, and that is equal to 2 into tan inverse capital D minus small d by 2h. So if we draw the if we find the values, okay, this will be capital D minus small d, this portion, and this this will be basically half of this one. This will be basically half of h, okay. This area, this will be basically half of h. Okay, so therefore uh sorry, this will be small h, this will be capital D minus small d, so this will be half of capital D minus small d. So therefore this angle basically equal to tan inverse of half of capital D minus small d by h. Okay, so 2 alpha will be 2 into 10 inverse half of capital D minus small d by small h. So that is the equation. Okay, so pull-out strength is calculated as the ratio of the force to the area of frustum, and the pull-out strength is correlated with the compressive strength of standard cubes and cylinders. So basically there are two types of pull-out test. One is lock test and one is capo test. So lock basically means punch in Danish language. So punch is basically, we are basically removing the chunk of concrete above it. So we are basically damaging. Okay, so punch basically means damage. So that's why it is semi-destructive. Okay, and so embedding the insert into fresh concrete while casting or by attaching it to formwork before placing concrete and then pulling out with a jack after hardening. So we are basically inserting it before the casting basically. Okay, and the application is for formwork removal, terminating, curing, etc. So that is basically lock test. And then there is capo test. So capo is abbreviation for cut and pull out test. Okay, and so this is without the need of pre-installed insert. Okay, so it can be post-installed. The insert is fixed into a hole drilled into the hardened concrete and then pulled out with a jack, and the application is quality assurance testing, evaluation of fire damage structures, testing in highly congested reinforcement area, etc. So this is the schematic diagram of the lock test and capo test. So these are the examples of field testing, of lock testing and capo testing, as can be seen here. And these are the instruments used for the test setup. Okay, as a test setup, basically in the capo. Sorry. So after performing a test, we basically get the pull out load. Okay, and using this we can compare with the uh, some already found out standard relations, okay, to find the strength. Okay, cylinder strength and cube strength. So these are the relations. Okay, these have been taken from some standard codes, basically I think from the ASTM C987. So the values are correlated. The pull-out load values are correlated with the compressive strengths of concrete cylinders that which are having 150 by 300 diameter into height, and 150 cubes basically. Okay, so those are related using this graphs, standard graphs. Then basically if we see here, this is the relationship between pull-out force and compressive strength of concrete. So this is in y-axis we have compressive strength, in x-axis we have pull-out load. So general consider correlations for cylinder and cube strength. If we see, these are the relations provided, and the factors influencing test results are basically the concrete condition and the equipment specifications. So that is all about the pull-out test. Now let us go into penetration resistance test. So it basically measures the hardness or penetration resistance of concrete. It is based on the principle that for standard test conditions, penetration is inversely proportional to the compressive strength of concrete. Penetration is measured over a certain depth, not just at the surface. The depth of penetration is correlated with compressive strength of concrete. The two types of tests are probe penetration and pin penetration, and it is done as per the ASTM C80390 standard. So here it is an example of penetration testing on concrete surface. So let us first start with probe penetration, and then we will go to the pin penetration. So probe penetration test, here the apparatus is basically powder actuated gun or driver, loaded cartridges for firing probes into concrete. The probe of hardened alloy steel with a blunt conical nose is used, and there is length measuring devices for measuring the exposed length of the probe. So this is the Windsor probe penetration test setup, and here experimentally this person is basically testing it on concrete. The probe penetration testing on concrete has been conducted. Okay, so this as per IR 7150, so this is the relation between 28-day compressive strength and exposed probe length. Okay, and these are the 95% confidence limits. That means 95% of the results will basically fall in between this region. Okay, so that is the confidence limit, and using this the equation is also provided, through which regression equation, so through which we can directly calculate without comparing the graph, without the need for using the graph. So here the probes are inserted by the gun driver, and then the exposed probe lengths are measured, which depends on the penetration resistance of concrete. They are correlated with the compressive strengths of concrete cylinders, which are basically 150 mm diameter by 300 mm height, or cubes having 150 mm side each. So that is the all about the probe penetration. Now let us go to the pin penetration test. So here the apparatus is basically a device that grips a pin of length 30.5 mm, diameter of 33.56 mm with an angle tip of 22.5 degree. The pin is held within a shaft encased within the main body of the tester. The pin is driven into the concrete by by a spring which is mechanically compressed when the device is prepared for a test. So this is pin penetration test setup, and this is the pin penetration testing on concrete. So if we see here again, as per Concrete International ACI standard, so here is a relation between pin penetration and compressive strength for two water cement ratios, 1.60 and one is 0.53, and both for block and cylinder. Okay, so pin is driven into the concrete, and after removal a small hole is created. Pin penetration depth is measured, correlated with the compressive strengths of concrete cylinders, 150 mm diameter by 300 mm depth, or tubes 150 mm. So that is about penetration and pin penetration, basically penetration resistance test. Now let us come to pull-off test. So this is to measure the in situ tensile strength of concrete by applying a direct tensile force, and also useful for measuring bonding of surface repairs, based on the concept that the tensile force required to pull a metal disc from the surface to which it is attached is directly related to the compressive strength of concrete, and it is as per the ASTM C1583 standard. So these are the loading conditions if we see here. So basically there are two types of pull-off test, sorry. One is surface and one is partially cored. We will study here what is the difference. So here the metal disc is attached directly on the concrete surface, as can be seen here. With application of load, only the surface concrete close to the face of the disc is stressed. Results indicate the strength of concrete near the surface. Then for carbonated surface, metal disc is attached on the surface of partial coring of certain depth. So in partial core, this coring is done. Okay. So what happens is, with application of load, concrete up to the depth of coring is stressed. So here the stress was basically only in this near the surface, but here it is up to certain depth until up till the coring is done. Okay, and results indicate strength of concrete up to the core depth. Okay, and for combining the metal disc with the surface, we basically use a epoxy resin adhesive. Okay, and this disc is basically the 50 mm, that is 5 centimeter diameter steel or aluminum disc. So that is the pull-off test. So the apparatus is cylindrical metal blocks, bearing ring or tripod that can be placed on the concrete surface concentric with the axis of the block. Then there is loading system capable of applying a force to the block normal to the concrete surface through the bearing ring or tripod. And then there is load measuring device capable of recording the maximum load after the force is released. So this is an example of a limpet equipment used in the pull-off test. The procedure is the disc is glued to the concrete surface with an epoxy resin and jacked off to measure the force necessary to pull a piece of concrete away from the surface. This causes tensile failure of the concrete. If surface carbonation or skin effects are present, partial coring up to a certain depth can be made. Pull-off tensile strength is correlated with compressive strength of concrete. The results cannot be directly equated to the tensile strength of concrete. So this is the pull-off test chart through which we can compare and find the 28-day compressive strength on the pull-off tensile strength. And this is the mean value, and this is the 95% confidence limit. So 95% results will be above. So this is the typical relationship between pull-off tensile and cube compressive strength of concrete with natural aggregate, and then they are related with compressive strengths of cylinders and cubes. So the core sampling and testing. So extraction of cylindrical cores from existing structures and testing in the laboratory to determine the so this is basically the next type of semi-destructive testing. So here, basically extraction of cylindrical cores from existing structures and testing in a laboratory is done. It is used to determine the in situ compressive strength of existing concrete. It is used to carry out chemical analysis and petrographic examination of concrete, and it is used for determining to the density of thicknesses of layers and their bonding characteristics, detecting the segregation and honeycombing within the material. The equipment uses core cutter with diamond impregnated bit, and the code is basically the Indian code IS 516 part 4 2018. So it is a new revised code. Okay, so basically petrography examination is basically analyzing a concrete sample under microscope, okay, and finding the minerals compositions and arrangements within the concrete matrix at a microscopic level. So this is the example of core sampling and testing equipments. So this is a core cutter here in site, okay. So inside, the extraction of concrete core using core cutter is done, and these are the core samples generated or developed, obtained. So here the core cutter should be rigidly placed and drilled perpendicular to the surface. Cores should preferably be taken from the middle portion and not near the edges, corners and joints. Drilling through reinforcement should be avoided. Should not be taken at locations with micro cracks, preferably from locations of compression zone. Results may be influenced by the core size, slenderness ratio, location of core extraction, reinforcement, curing condition, etc. So the core diameter generally ranging from 100 mm to 150 mm for nominal maximum aggregate size up to 20 mm. The preferred core length per diameter L by D is equal to 2. If L by D is less than 2, a correction factor is used. Core surfaces must be grinded to make the surfaces flat and parallel for testing. The tolerance is plus minus 0.05 mm. Cores need to be capped with calcium aluminate cement, mortar or sulfur sand mixture before testing. Cores should be tested in saturated condition. So if we see after obtaining the cores, okay, so the compression test is done and the rate of load application is 14 Newton per mm square per minute. The compressive strength is equal to maximum load by cross-sectional area, and the failure pattern is to be noted. So here it is an example of how the placing of core is done in CTM, and this is the lab setup. Okay, so this is the setup used for the finding the compressive strength of the cylindrical specimen. So correction factor F based on core diameter for cylinder compressive strength is provided here. So for a diameter of core of 75 plus minus 5 mm, we use a correction factor of 1.03, and less than 70 mm we use 1.06 factor. And the correction factor based on L by D ratio for cylinder compressive strength is F is equal to 0.11 L by D plus 0.78. That means if the L by D value is 2, okay, so F will be equal to 1, okay. But if it is less, it will be less, and if it is more than 2, it will be higher, okay. So the equivalent cube strength of the concrete can be determined by multiplying the corrected cylinder strength by 5 by 4. So the result obtained, it is for cylinder strength. If we multiply it with 1.25 or 5 by 4, we will get the cube strength. So these are the assessment of failure pattern, okay. So and it is very important in core testing. So these are some of the examples of unsatisfactory failures, okay, of cores, and these are the some of the examples of satisfactory failure of cores, okay. So these are the typical cores after testing. So here in this lecture, we basically studied the semi-destructive testing, where we studied the pull-out test, penetration resistance test, pull-off test, core sampling, and testing. So the next lecture, basically, it will be on non-destructive test. So the previous lecture was on SDT, that is semi-destructive. Now we'll be studying the non-destructive test. So here the concepts covered will be basically the basic two tests, okay, which are quite popular. One is the Riemann hammer test, and one is the ultrasonic pulse velocity test. So these are quite popular because they are non-destructive testing, okay. So it can be used anywhere without any concern of any damage happening. So these are the in situ tests conducted, okay, on existing structures using specialized equipment. It is used to determine the property, condition, and durability of the material or structure without damaging it. The results are correlated with the results of other destructive or non-destructive tests. The results may be affected by environmental conditions, construction details, and building components may affect the results. Generally, more than one test method is required to estimate or assess the quality of material and condition of structure. So it is basically affected by environmental conditions. So and also construction and building components used and details used. So that's why it is always important to validate the results with more than one test, either destructive or non-destructive or semi-destructive. So firstly we'll be going through the rebound. Firstly, we'll be going through the rebound hammer test. So this test is basically used to measure the hardness of concrete surface by rebound principle in laboratory and in field. It is used to determine the compressive strength of existing concrete by correlating with its surface hardness. The instrument uses Smith 1948 outer body plunger, spring driven steel hammer mass of 1.8 kg, abrasive stone silicon carbide. It is very inexpensive, simple and quick method, and it is done as per the IS 516 part 5 section 4, which has been revised in 2020. So this is the example of the Smith rebound hammer used. So that was basically invented by a person called Smith in 1948. That's why it's called Smith rebound hammer. So the test procedure is such. Firstly, the plunger of the rebound hammer is pressed against the concrete surface. After releasing, the hammer strikes the plunger and the spring controlled mass rebounds. Based on the rebound distance, a rebound number is produced. A rebound is read on a linear scale marked from 10 to 100 or on an electronic display and is termed as rebound number or rebound index. The extent of rebound depends upon surface hardness of concrete. Harder surface gives higher rebound. Concrete with higher compressive strength generally has harder surface. So this is basically the schematic diagram of the working principle of rebound hammer. So as you can see here, we basically firstly hammers in this position. It is the starting rest position. Okay, rest position for hammer, which is ready for test. So here basically this plunger. Okay, so this is pressed against this surface. This is the concrete surface. So after that, the after pressing it to the full. Okay, so when the body is almost touching the latch. Okay, so at that point the hammer is released. Okay, so this is the hammer basically, and this hammer basically strikes the uh, basically it strikes the body, okay, the top of the body, and it again rebounds. Okay, so based on that a rebound number is given in this indicator, and based on that we get the we can correlate that number with the compressive strength. So this is an example of testing with rebound hammer on site. So the test considerations are: surface should be clean, smooth and dry to be rubbed off with the abrasive stone. Point of impact should be sufficiently away from edges or shape discontinuity. Rebound hammer should be held firmly at right angles to the surface of concrete. Should be conducted all around the points of observation on the accessible faces. At least 5 to 6 reading to be taken, and the average of these readings is to be considered as the rebound number for the point of observation. So the correlation between rebound number and compressive strength is shown here. So it is determined by comparing with the compressive strength of concrete cubes 150 mm or cylindrical cores 150 mm diameter by 300 mm depth of the same material to be tested with rebound hammer. It is conducted horizontally or vertically, upward or downward. So the relationships between compressive strength and rebound number are shown here. So this is the rebound value, and this is the string, and here it is the dispersion. So if you see, when the plunger is down, okay, so it is vertically down, so it gives the maximum value. When it is horizontal, it is giving intermediate strength, and when it is upward, okay, vertically upward, it is the lowest. Okay, So the factors which influence these results are smoothness of surface under test, surface and internal moisture content of concrete, curing and age of concrete, size, shape and rigidity of the specimen, type of aggregate, type of cement, carbonation of concrete surface, vertical distance from the bottom of concrete placement, surface conditions used in development of correlation between compressive strength and rebound number. So rigidity is basically inability to be bent, to be or be forced out of shape. Okay, so that inability is rigidity. Okay, so some important points during the rebound hammer test are: open texture concrete typical of masonry blocks, honeycomb concrete or no fines concrete are unsuitable for this test. A wet surface will give rise to underestimation of the strength of concrete. Calibrated under dry conditions, nearly 20% lower. Rebound indices are indicative of compressive strength of concrete to a limited depth from the surface. If the concrete in a particular member has internal micro-cracking, flaws or heterogeneity across the cross-section, rebound hammer indices will not indicate the same. So some important points should not be considered as a substitute of standard compression test applicable to assess the in-place uniformity of concrete, to delineate or map out the regions in a structure of poor quality or deteriorated structure concrete. So these are the practical examples of testing done with rebound hammer, okay, or the rebound hammer test. Now let us come to the UPVT or ultrasonic pulse velocity test. So this is a qualitative assessment of strength of concrete. It is used to assess the condition of structural members on the basis of recorded ultrasonic velocity. It is used to evaluate the internal cracks, voids, delamination, and other damages in concrete, mortar, wood, masonry, ceramic, and metals. It is used to detect the deterioration due to aggressive chemicals or environmental effects, and it is also used to evaluate the severity of deterioration. So delamination is basically separation or detachment of a thin layer of concrete peeling away from the main slab. Okay, so that is a type of spalling. Okay, so spalling is basically a large layer and delamination is basically a thin layer. So here it is a practical example of UPV testing on concrete being done. So the principle of test is as follows. It basically follows the wave propagation theory. So when the surfaces of a solid elastic medium is affected by dynamic or vibratory load, there are three types of mechanical waves created. Okay, so it is almost like the earthquake. Okay, it is almost like the earthquake, but here the L wave is not present. That is basically the love wave. Okay, apart from that, all the three waves are present, which are the compressional waves or the longitudinal P waves, the shear waves, which are the transverse S waves, and surface waves, which are the relic waves. So if you remember, the S waves or the shear waves are the main waves which basically causes the damage in earthquake. Okay, because they are vertically. Okay, so that wave. Okay, so that is basically going vertically. Okay, so it the surfaces are like the ground. Okay, it is shaking up and down. However, the P wave, which is the initial wave, primary wave, so that the flow is basically it is horizontal. Okay, so it is propagating horizontally. So that's why the damage is very minimum. Okay, so main damage is basically happening due to the S wave. Okay, in earthquake. And the relic wave, it is basically a partial S wave where it is basically surface wave. So the shear phenomenon occurs basically only in the surface, not throughout the medium. Okay, of the solid elastic medium of the soil. Okay, so basically that is the principle. So each wave propagates with its characteristics velocities. The wave velocity depends on the elastic properties and density of the medium. For elastic homogeneous solid medium, the compressional wave velocity is expressed as v equal to square root of e into 1 minus mu by rho into 1 plus mu into 1 minus 2 mu, where e equal to dynamic modulus of elasticity, mu is equal to dynamic Poisson's ratio, and rho is equal to density. So in UPV test, an ultrasonic pulse velocity, a pulse wave is generated by the transducer held in contact at a point on the surface of the test object. After traversing a known path length L within the material, the pulse of vibrations is converted into an electrical signal by the second transducer which is held in contact with the other surface of the member. So basically transducer are those equipments which basically convert as a signal, okay? So from electrical signal to a vibration signal, or vibration signal to a electrical signal, okay? So that, so it basically it is used basically in the UPVT test. So now the distance between the 2 points L and the time of travel T from that point to another, using that, the velocity of the wave pulse uh, basically can be determined, that is using the simple concept V equal to L by T. So reflection and refraction occurs when sound waves interact with interfaces of different acoustic properties. So acoustic properties are the characteristics of materials and structures that affect how sound waves travel through them. So here, this is the example of the UPVT setup. So this is the actual photo of the UPVT test setup, and this is the working principle. So if you see here, this is the transmitting re transducer, and this is the receiving transducer. And to work, basically, we are giving a pulse generator, and basically we are receive. This is the pulse generator, this is the receiver amplifier, and this is the time display unit. So both the pulse and receiver, it goes to the time measuring circuit, and then the time display unit is generated, and through that we basically get the velocity, okay? We can calculate the velocity. So a pair of transducers for pulse generator and pulse receiver. As I told you, transducer is an electronic device that converts energy from one form to another, here between the pulse of vibrations and an electrical signal, okay? So apart from that, we need the display unit, the calibration rod, okay? So this is the calibration rod, and the cables here, and the gel, okay? So this gel is used so that there is basically uniform surface for the transducer to operate. So there are three types of UPVT tests. That is the three types of transmission. One is the direct transmission, which is a standard one. And apart from that, for various constraints, we can also use the semi-direct transmission or the indirect transmission. Okay. So as you can see here, so L is different for all the cases. Here it is simply the length between the two points. In the case of semi-direct, it is square root of a square plus b square. That is the it is basically the hypotenuse. And in the indirect or surface tension, the L is again the points, horizontal distance between the points, okay? So the pulse velocity V is equal to capital L by capital T. So once the ultrasonic pulse impinges on the surface of material, the maximum energy is propagated at right angles to the face of transmitting transducer. Thus base results are obtained for direct transmission or cross probing. Semi-direct and indirect or surface probing not as efficient as cross probing. Signal produced at the receiving transducer has amplitude of only 2 to 3% of that produced by cross probing. These results are influenced by surface layers, which may have different property from inner materials. Indirect velocity is thus lower than the direct velocity of same concrete. For surface probing methods, pulse velocity may thus be increased by 0.5 km per second for values greater than equal to 3 km per second. So that is the reason why we should always go for direct transmission. That is the first one, okay? Others are not as efficient, and they are basically it has various defects, problems, okay? But because of various constraints, we have sometimes we have to go, okay, uh, for the other two options as well. So as you can see here, so here it is the base case, which is the direct method. But in this case, say for example, in the case of a wall, okay, so we only have to use the indirect method. And in some cases where the other one side of the beam, one one vertical side of the beam is not attainable or not reachable, we have to use the semi-direct method. So because of various constraints, we have to go for the other two as well. So and this is basically the chart through which the quality is being noted of the concrete. So it is given in IS 516 part 5 section 1, and it is revised in 2018. So if the pulse velocity is greater than 4.4 kilometer per second, it is considered a it is the grade of concrete is excellent. Between 3.75 to 4.4, it is considered a good concrete quality. From 3 to 3.75, the concrete is doubtful, and less than 3.0, it is poor. So higher velocity is obtained when concrete quality is good in terms of density, uniformity, homogeneity, etc. If there is a crack, void or flaw inside the concrete which comes in the way of transmission of the pulses, the pulse strength is attenuated and it passes around the discontinuity, thereby making the path length longer. So consequently, because L by T, so V is directly proportional to uh, T, right? V is directly proportional to L, right? So the pulse strength is attenuated and it passes around a discontinuity, thereby making the path length longer. So consequently, lower velocities are obtained. So basically, more than the length, the time increase will be much more. Okay, so T is very much higher as compared to the increasing length. So therefore, the velocity is decreasing instead of increasing. Okay, so that is the reason. So then the factors affecting pulse velocity, here the contact between the transducer and the concrete it affects. So that's why we basically use the gel. Okay, so as you can see here, this gel. So that is basically for making it efficient. The contact, okay, between the transducer and concrete. Then there is path length. Okay, so that is fixed L. Size and shape of member, moisture content of concrete, temperature of concrete, presence of reinforcing bars, stress to which the structure is subjected, and presence of cracks and voids. So these are the examples of rebound hammer and UPV testing on a concrete deck slab from its bottom done. And so that is all about the UPV and rebound hammer test which we discuss in this lecture. Okay, so those were the examples of non-destructive testing. So in the next lecture also we'll be continuing NDT. So here we will basically be covering four types of more NDT. Okay, so one is electromagnetic cover measurement, one is half cell potential measurement, one is resistivity measurement, and one is carbonation depth measurement. So a number of NDT tests related to corrosion of embedded steel reinforcements are present. To detect the corrosion potential, the rate of corrosion and the extent of corrosion on steel reinforcements is required. Tests used in combination for detecting corrosion can be electromagnetic cover measurement test, half cell potential test, resistivity test, carbonation depth measurement test. So basically these NDT tests are basically related to corrosion. Okay, so that's why a separate lecture was given for those for them. So let us first start with the electromagnetic cover measurement. So electromagnetic methods commonly used to determine the location of steel reinforcements and the depth of its cover within concrete. So they are based on ferromagnetic principle which is applicable for ferromagnetic materials. Okay, so this have magnetic properties. Okay, iron have magnetic properties. So the basically the basic principle is that the presence of steel affects the field of an electromagnet. So that is due to electromagnetic induction, okay, as per Faraday's law. And it detects a bar by briefly magnetizing it, then registering the magnetic field as it tapers off. So as the field becomes weaker or less frequent, based on the change in magnetic intensity, okay, so the bar can be detected using a instrument. Okay, so the test principle, the test equipment circuitry resembles a simple transformer in which the test object acts as a core. Electrical circuit consists of a primary coil connected to a power supply for delivering a low frequency alternating current, a secondary coil which feeds into an amplifier circuit. So alternating current is basically here the electrons basically change their path. Okay, so change their path to and fro. Okay, in absence of a test object, the primary coil induces a small voltage in the secondary coil. So in presence of a ferromagnetic object near the coil, a much higher secondary voltage is induced. Amplitude of the induced signal is a function of magnetization characteristics, location and geometry of object. So this is the working principle of electromagnetic cover measurement as can be seen from these two figures. Okay. So the instrument uses cover meter, which is a battery operated device. It utilizes the eddy current method of magnetic testing. This method induces eddy currents to flow around the circumference of the bar, producing a magnetic field. The head of the device picks up the magnetic signal. So eddy currents are loops of electrical current induced within conductors by a changing magnetic field in the conductor according to Faraday's law of induction. Eddy currents flow in closed loops within conductors in planes perpendicular to the magnetic field. So detection of reinforcement and cover depth using cover meter, as you can be seen here in practically experimentally live at site. And so that is all about electromagnetic cover measurement. Okay, so the next test for corrosion detection is half cell potential measurement. So this is a method used to identify the likelihood of corrosion in steel, its location and extent. Corrosion potential of reinforcement is measured as a potential difference against the reference electrode, which is called the half cell. The value of the potential difference between steel and the reference electrode depends upon the corrosion condition of the steel and the type of reference electrode. Half cell potentials of steel in concrete cannot be measured directly at the concrete or steel interface due to the presence of concrete cover. Okay, so that is one of the disadvantage. So now let us see the test principle. When there is active corrosion, the flow of current ion migration between the anodic and cathodic regions is accompanied by an electric potential field surrounding the corroding bar. The equipotential lines intersect the surface of concrete. The potential at any point can be measured relative to a reference half cell placed on the concrete surface, which functions as an electrolyte. The risk of corrosion is then related to the measured potential difference, and the portion for likelihood of corrosion is identified by their high negative potentials. So this is the working principle of half cell potential measurement. Okay, so the and the cathode basically so basically the positive terminal is connected to the concrete rebar, and the negative terminal is basically connected to the half cell. Okay, so this is basically the anode and this is basically the cathode. Okay, the negative. So here this is the disadvantage, so you cannot directly connect it to the cover. Okay, you have to remove the cover and directly then only you can connect it with the reinforcement. So the reference electrode can be of three types. One is copper sulfate electrode, which is shown here, so that is CSE. One is silver chloride electrode, which is SSE, and one is standard calomel electrode, which is SCE. So the instrument basically it consists of half cell connecting wires, high impedance voltmeter. So this voltmeter can basically measure opposition to electrical flow, which is impedance. Okay, high level of resistance. Okay, so generally greater than 10 mega ohm. Okay, so which is a very high resistance. Half cell, it is a copper bar immersed in a saturated copper sulfate solution. The positive terminal of the voltmeter is attached to the reinforcement and the negative terminal is attached to the half cell. The half cell makes electrical contact with the concrete by means of a porous plug and a sponge to be moistened with a wetting solution. If the bars are corroding, the excess electrons in the bar would tend to flow from the bar to the half cell. A negative voltage is indicated in the voltmeter. So the data is acquired at various test points for the display of equipotential contours. It is created by locating the test points on a scale plan view of the test area. Contours of equal voltages are generally drawn into an interval not more than 100 millivolt. A more negative voltage reading at the surface is interpreted as the embedded bar has more excess electrons, that is higher likelihood that the bar is corroding. So more excess electrons means the bar corrosion has a higher likelihood, and this is as per the ASTM C876. So as you can see here, the equipotential contours. So the contours are basically lines having the same value. Okay, so if you see here the semicircle type of lines basically, so these are the current lines. Okay, and the straight the lines coming from a point. Okay, radiating from a point, they are basically the equipotential lines. Okay, so these lines are equipotential lines and these are basically the semicircle lines are basically the current lines. Okay, so this is the live example of half cell potential measurement being done, and this can be seen here, and based on this we get the half cell equipotential contour map. Okay, so that is basically equipotential, this lines which have been radiating from a single point. Okay, so these areas have the same potential value. Okay, equipotential value. So the risks of corrosion against the potential difference reading for the copper sulfate electrode. So potential difference levels is between minus 350 to minus 500 millivolt. Then the chance of rebar being corroded is 95%, very high chance. If it is between minus 200 to minus 350 millivolt, then the chance of rebar corrosion is 50%. And if it is greater than minus 200, okay, or in absolute terms less than 200, so the chance of rebar corrosion is very less, around 5%. The access to reinforcement is necessary for the test, so this is one of the big drawbacks. Concrete surface should be sufficiently moist to complete the circuit, cannot be applicable for epoxy coated reinforcement or concrete with coated surfaces, because then we will be getting very different values. So half cell potential tests on concrete deck slab and girder. As I told you, girder is a section which is having a very high modulus of inertia, I value. Okay. So now let us come to the next test, which is the resistivity measurement. So this is a useful test to measure the resistivity of concrete in conjunction with half cell potential method to assess the corrosion rate or risk. Half cell potential method gives an indication of the likelihood of corrosion activity and is effective in locating regions of corrosion activity but not the rate of corrosion. Rate of corrosion depends on, after a bar loses its passivity, the availability of oxygen for the cathodic reaction to occur. So if you remember cathodic reaction, so that is basically the production of hydroxide. Okay, so from here the hydroxide went, and from the anode the Fe2 plus, okay, so it came, and then Fe2 plus OH minus, it became FeOH2 and FeOH3. That was basically rust. Okay, so for cathodic reaction OH minus formation, oxygen is required. Okay, so rate of corrosion depends on the availability of oxygen for the cathodic reaction. The electrical resistance of concrete is also important. So the electrical resistance of concrete controls the ease with which the ions can mine. Sorry. So the electrical resistance of concrete controls the ease with which ions migrate between anodic and cathodic sides. I'm sorry. A higher resistance path between anodic and cathodic sites normally associated with a lower rate of corrosion. Resistivity measurements determine the current levels flowing between anodic and cathodic portions, or the concrete conductivity over the test area. Electrical resistance depends on the microstructure of the paste and the moisture content of concrete. So basically, resistivity is inversely proportional to corrosion. A higher resistance path signifies a low rate of corrosion, and so these measurements basically determine the current levels flowing between the anodic and cathodic portions, or the concrete conductivity over the test area, right? So in this test, basically we basically use a 4-probe resistivity equipment. So this is the example of uh, practical evaluation of the resistivity. So based on the resistivity value, we basically can relate uh, the corrosion current. Okay, so it can be done using this as shown here. So there is a relationship between concrete resistivity and corrosion current. So resistivity is numerically equal to the electrical resistance of a unit cube of a material, and the unit of resistivity is resistance times length, that is ohm centimeter or k ohm centimeter. So resistance R of a conductor of area A and length L is related to resistivity rho as R equal to rho L by A. So this is very standard physics, okay, related to electricity. So R is equal to rho L by A. So if we see here the testing principle, so this is the working principle of resistivity test. So if you see here, these are the current flow line, these are the equipotential lines, and here the AC supply is going, and this is the current measured by a meter. Voltmeter measures the voltage, and electrodes with couplant. Okay, so couplant is a material basically that helps transmit ultrasonic energy from a transducer to a test object, and they are often used in ultrasonic testing to fill in gaps between the transducer and the object being tested. So here it is concrete. A low frequency alternating electrical current is pass between the two outer electrodes, whilst the voltage drop between the inner electrodes is measured. So current is passed between the outer electrodes, and the voltage between the drop between the inner electrodes are measured. Okay, the apparent resistivity rho is calculated as rho equal to 2 pi SV by capital I, where S is equal to electrode spacing, V equal to voltage drop, and I equal to current. Okay. So here the instrument basically uses a resistivity meter, which is a Wenner 4-probe resistivity meter. So as you can see here, so this is the photo. The equipment consists of 4 electrodes, 2 outer current probes and 2 inner voltage probes, placed in a straight line at a spacing of 50 mm or 5 cm. Spacing of the 4 probes determines the regions of concrete being measured. A low frequency alternating current passing electrical current is passed through between the outer 2 electrodes, while the voltage drop between the inner electrodes is measured. Pre-wetting the concrete surface desirable to have better electrical contact using water or conductive gel. Resistivity is influenced by moisture content, salt content, temperature, water cement ratio, and mix proportions. So as you can see, these are the live examples of resistivity tests on concrete girder, as can be seen here using the resistivity meter. Next, we will study basically on the carbonation depth measurement. Okay, so it is used to determine the depth of concrete affected due to carbonation as a result of reduction in the level of alkalinity and degradation. Carbonation of concrete occurs due to increase of atmospheric CO2 and reaction with calcium hydroxide present in concrete in presence of moisture to produce calcium carbonate. So CaOH2 plus CO2 gives calcium carbonate basically. And the carbonation causes depassivation of reinforcing steel when the pH becomes less than 9 basically. So around 10, between 9 and 10, the depassivation is removed. Carbonation penetrates the exposed surface of concrete very slowly, and phenolphthalein is used as an indicator for the pH of concrete. If you see here, so if you remember chemistry classes, so basically phenolphthalein, it changes its color from this magenta color to colorless, okay, when there is a reduction in pH. So around 12, okay, so around 12 the color is magenta, and then it starts changing its color, and below 9 and 8 it becomes colorless. So if it is colorless, it means the pH is less than 9 or 8, so that means this carbonation has occurred, okay, and that has basically reduced the pH and the depassivation of the reinforcements. So basically the phenolphthalein for testing process, the phenolphthalein solution is prepared where 1% phenolphthalein solution is basically made by dissolving 1 gram of phenolphthalein in 90 cubic centimeter or 1 ml of 90 ml of ethanol. The solution is then made up to 100 ml by adding distilled water. Okay, so that is 1% phenolphthalein solution, and then uh, basically then core is extracted, and the phenolphthalein solution is sprayed on the freshly extracted cores as pH indicator of concrete. Can be conducted by drilling holes on concrete surface and by removing the dust. The depth of uncolored portion receives the depth of carbonation. Okay, so these are the cores after carbonation test. So if you see, these part are carbonated. Okay, so the change in color of concrete to purple indicates concrete still retains its alkaline characteristic, no carbonation. As I told you, no changes in color indicates acidic characteristics with reduction in pH. This part, as I told you, is carbonation has taken place. Depth measurement at 4 to 8 locations and the average is taken. Okay. So carbonated zone pH less than 9, non-carbonated zone pH greater than 12. The challenges, so these were basically the NDT tests related to corrosion. Okay. So all NDT methods are indirect. The all NDT methods are indirect. The correlation needs to be developed between measured parameters and material strength or other properties based on destructive test results. Require they require specialized equipment. Instruments are expensive, require limited manpower but trained manpower for carrying out the test. Results are dependent on too many parameters. Interpretation of results is not straightforward and requires strong judgment. So these are some of the issues, okay, with this and non-destructive tests. Okay, So in this lecture we basically covered the four entity tests. So they were the electromagnetic cover measurement, uh, the half cell measurement, potential measurement, the resistivity measurement, and carbonation depth measurement. Okay. So now let us go to the next lecture, which will basically talk about the other basically tests. So here we will be basically studying the petrographic tests. Okay, so tests which are conducted for the microstructure. So as I told you, so we'll be covering petrographic analysis and load testing of existing structure. So petrography is basically a branch of geology that is applied to rock and similar materials, concrete and concrete raw materials. This technique examines and evaluates the optical properties and microstructural characteristics of the materials. It is like pathology test for any material. So pathology is the study of essential nature of diseases, especially for structural and functional changes produced by them. So that is mainly for human body. So uh, it is for the concrete body. Okay, so it is like pathology test for material. Okay. Petrography involves the use of a variety of microscopical techniques like SAM, like stereo microscopy, polarizing microscopy, fluorescent microscopy, metallurgical microscopy, and electron microscopy. So that can be of SAM, that is scanning electron, and TEM, that is tunneling electron microscopy. Okay. So these are used for submicro examination or microstructural properties. And for example, this is a 220 micrometer thick fluorescence impregnated thin section in ultraviolet light. Okay, so it is studied under UV light. So the identification of ingredients used, such as types of cement aggregates and cement replacement materials. Okay, so it is done here. Estimation of original mix proportion, for example cement content, aggregates content, and water cement ratio is done. Determination of air void content, which includes entrained air and entrapped air. Investigation of chemical and durability performance, like chemical attack, alkali silica reaction, aggregate or cement paste shrinkage, frost attack, carbonation, leaching, detection of unsound contaminants, and fire damage. So here this picture shows plain polarized light micrograph of alkali silica reaction ASR induced cracking. Okay. So these are some of the equipments used for the petrography analysis. So this is the petrographic polarizing microscope. So this is used for low to higher magnification examination of thin sections and small particles of rock, soil, concrete, cement, grout, etc. for taking photo micrographs on the order of fractions of a millimeter. And this is the example of low power stereo microscope. So this is used to determine the air void content, including entrained air and entrapped air. Then there is reflected light microscope. So it is used for top light illumination. Illumination is basically the light. Okay, to examine polished specimens of rocks, concrete, cement, grout, etc. And the light is given from the top basically, and may be also used for identifying opaque materials, opaque minerals. Sorry. Then there is XRD. Okay, it is an abbreviation for X-ray diffraction or diffractometry. So X-ray bombardment of a powder sample, and then measuring the intensities and scattering angles of the X-rays that leave the material, identify the crystalline phases present in a material, and thereby reveal chemical composition information. Okay, so that is about the XRD, and this is the example of an XRD analysis. Okay, then there is scanning electron microscopy or SEM. So it produces images with very high magnifications. It is used to analyze both crystalline and non-crystalline materials. It can provide detailed images of very small particles on a submicron scale and provide their elemental compositions, which is basically EDX. Okay. Then there is a specification of specimen. Okay, so the thickness of the thin sections 25 to 30 micrometer. It can be geological, petrological, mineralogical examination of rocks. Uh, so here these are examples of core cutter and thin section sampling, and here it is basically the thin sectioning system. Okay, and this is the preparation of cast thin section of concrete, and here it is the variable speed grinder polisher. So these are used in SEM. Okay, SEM preparation, SEM material preparation for SEM analysis, scanning electron microscope. Then the information needed to be provided for each specimen is location of the core taken, orientation of the core, age of the structure, reasons and objectives of the examination, including the observed symptoms of deterioration of the structure. So these are the information required. Okay. Then the investigation of durability of concrete, basically. So it can be done using the petrographic analysis for external sulfate attack, delayed attringite formation, then alkali silica reaction, acid attack, carbonation induced corrosion, chloride induced corrosion, and shrinkage. So these are some of the investigations for which it can be investigated. So these investigations can be done using petrographic analysis. And so this is the sulfate attack basically. So that has been found using the SEM. So you can see the cracks. Okay, and this image, these are basically, in this image the attringits are shown here. So these are needles basically, okay, of attringits demonstrating porous volume. So SEM image analysis, the parallel surface cracks, presence of gypsum and attringite, depletion of calcium hydroxide, decalcification of calcium silicate hydrates, etc. Then the internal sulfate attack, so like delayed attringite formation, we studied about it in the last class, DEF. So the presence of gaps completely encircling the aggregates, wider gaps around large aggregates than around small aggregates, absence of an external sulfate source, documentation of the use of high temperature during the curing phase or mass concrete pours. Okay, so here if we see, these are the formation of gaps between aggregates and cement paste. The texture of surface attacked by sodium sulfate. The zone of sulfate attack contains an extensive system of fine cracks that form an exfoliation texture. Many of the cracks are filled with crystals of gypsum. Then there is alkali silica reaction. So optical microscopy and SAM EDS analysis. Presence of alkali silica reactive aggregates. Nature of the crack pattern. Presence of alkali silica gel in the cracks. Presence of calcium hydroxide depleted paste. So this can be obtained, say for example, using this case, if you see the photo using an optical microscope, one is non-polarized left and other is polarized light. Okay, in the right. So polarized light is basically the light in which basically polarized light, in the polarized light the rays are basically uh, they're basically propagating in a single direction. Okay, so they are not propagating in random directions, so that is polarized. Okay, and uh, so here if you can see here, various elements have been, various minerals have been detected, like quartzite fragment, okay, damaged by several cracks, partly inlaid by alkali silica gel, like quartzite rock fragment, monomineral quartz fragment cracks, cement paste alkali silica gel, okay, partly inlaying a crack. So various types of cracks and various components and mineral compositions have been detected using the microscope. Then there is carbonation. Okay, so if we see here, in section views showing the deeper penetration of carbonation along cracks and other discontinuities in two concrete samples. So A is buff colored carbonation and B is crack filled with yellow dyed resin bordered by orange brown carbonation. So it can be seen here. Then there are shrinkage cracks. Okay, so examples of aggregate shrinkage in concrete in thin sections. Peripheral cracks infilled with yellow dyed impregnating resin. A concrete from Puerto Rico. So this is in Brazil. And B concrete from Northern Ireland. Okay, so this has been used. This has been done using fluorescent microscopy image. Okay, so fluorescence is basically a phenomenon that is releases light when electrons are excited, and then it again after excitation it emits. Okay, so when the energy is emitted, so that basically uh, Like when it comes to the again the ground state, it emits the energy, so that emission basically gives the fluorescence, okay, that color. Okay, so that is the fluorescence process. So using that concept, the microscope which uses that concept is the fluorescent microscope. Okay. Then the chloride induced corrosion. So here the same image analysis, incorporation of chloride into passivating film of steel reinforcement, debonding of passivating film. So here if we see, it is the same micrograph showing the incorporation of chlorides into the passive film. Okay, so how the chlorides are attacking the passive film, okay, or depassivating the steel. Okay, now let us come to the next topic, which is the load testing of a structure. As the built environment is aging, assessment of existing structures becomes increasingly important. Load testing an effective means of evaluating the structural response non-destructively. So load testing is effective means of evaluating the structural response non-destructively. The purpose of load testing of structure is when the integrity of the structure is in question, if the structure will be used for a new function with higher loading after uh, exposure of the after exposure of the after exposure of the structure to an extreme load, to evaluate the structure after repair and retrofitting, to calibrate uh, analytical models of existing structures by obtaining field data of load testing. So these are the purposes of load testing of structure. So here basically we calculated TLM, which is the test load magnitude as per the ACI 437.213. So this includes dead load, live load, snow load and rain load with their combinations. Using load factors, structure is loaded with test load magnitude TLM. So TLM is equal to 1.3 into dW plus ds. TLM equal to 1.0 dW plus 1.1 ds plus 1.6 L plus 0.5 LR or S or R, and TLM equal to 1.0 dW plus 1.1 ds plus 1.6 into LR or S or R plus 1.0 L. So basically when only uh, dW, that is load due to self weight of the concrete structural system, and ds, the superimposed load, dead load including construction materials, fixed service equipment, etc. So when both are only both these two are present, we use the first equation. Along with that, when there is this along with that when there is your L is live load due to S use or and occupancy of the building. Okay, live load. LR is roof live load produced during maintenance by workers, uh, workers equipment or materials, or during the life of structure by movable objects such as planters and people. So the roof live load is LR, and S is snow load, and R is rain load. So basically both equations can be used, okay, based on the requirements provided by the ACI. So only dead load and superimposed dead load is present, we use the first equation. And apart from that, when there is life load, roof life load, snow load and rain load, we use the two equations, the other two equations based on the necessity or the requirements as per the standard code. So the monotonic load testing and cyclic load testing. Structure is loaded with TLM monotonically or cyclically and then unloaded. Load is applied using hydraulic jack, stacking of mass, mobile test vehicles, static loads on vehicles, etc. Response of the structure like deflection, strain, rotation, crack, width, etc. during or after the test is monitored and recorded continuously or intermittently using dial gauges, LVDTs, deflectometers, strain gauges, crack meters, FOS, total station, etc. Okay, so these are some of the uh, basically methods used. Okay, so total station measures the horizontal and vertical angles as well as the distance between specific points on the structure. Structure is considered satisfactory if the responses are within acceptable limits. So here we will see the monotonic load testing protocol. So loading the structure in a monotonic manner by gradually applying the load until reaching the TLM, that is test load magnitude, which is maintained for 24 hours. So this, okay, at least 4 equal increment of load application, so 25% increase every time. And your this one, each load step to be held for at least 2 minutes, okay, for stability. Deflections are recorded at each load step, and after that TLM, to test load magnitude, to be removed quickly. So here it is monotonic load testing protocol as per ACI 437.213. Then there is cyclic load testing protocol. So here repeated application of loading and unloading the structure by applying loads in increments. Multiple cycles of incremental loading and unloading until reaching the TLM. Each load step to be held for at least 2 minutes. Reflections are recorded at each load cycle. Load to be applied without impact and without causing vibration of the structure. So these are some of the conditions for the cyclic load testing protocol as per ACI 437.213. Then, so what is the acceptance criteria? Okay, for the structure to pass the load test, the residual deflection, that is delta R, should be less than equal to delta L by 4, where delta L is the maximum deflection, which is less than equal to LT by 180. Okay, so LT is basically free span of the member under load test, okay, in inches, and to be recorded during 24-hour load hold. Okay, so free span is between the two supports. Okay, so so in between there are not supports, okay, in the free span. So at the end only their supports are provided, that is free span. If uh, uh, so if the measured delta R, okay, so that is the residual deflection, not it is not satisfying its limiting criterion, but the measured delta L, that is maximum deflection, it satisfies its limiting condition, then repeat test is permitted. Okay, so that is the condition. Okay, otherwise if this is also not satisfying, that means the structure is the structure is not acceptable, the structure is not acceptable, and complete this has to be done, retrofitting has to be done. So uh, for the structure to pass the repeat test, so if the delta R value is less, so the structure has to we can perform the repeat test. So the for the structure to pass the repeat test, the residual deflection of the repeat test, that is delta RRT, so that is less than equal to delta L2 by 10. Okay, so delta RRT is equal to permanent or residual deflection measured after the 24-hour recovery period following complete removal of the load at the completion of repeat load test, and delta L2 is equal to maximum deflection measured from the repeat test. So these are as per the ACI codes. So apart from that, there for bridge, okay, so there are stages of load testing of bridges which have been provided as per IRC SP 51 2015. So those stages are basically selection of the critical span, selection of type of load test and method of loading, selection of instruments for the measurement of responses, placement of sensors and instruments, calibration of instruments, mobilization of personnel and testing agencies, application of loads and recording the responses, supervision and quality assurance, check for the acceptance criteria, retesting if required. Okay, so these are the stages for load testing of bridges. The precautions for load testing of bridges are: one, all staging should be stable and safe. Two, staging for instruments and observers should be independent and rigid. Three, safety staging may be erected depending on the site and traffic condition. Four, contact between the sensors and the structure should be maintained. Five, temperature and weather conditions to be noted. So these are the precautions for load testing of bridges. So this is a live example, practical, realistic example of a load testing of a flyover using big trucks. Okay, so these are the trailer trucks, lorries. These are basically used for the bridge health check. Okay, so these are the measurement of the responses underneath the bridge, as you can see. So with this, we come to the end of this lecture and also this week's course. Okay, this week's lecture, this week's content basically. So now let us start with the problems. Okay, understand better. Let us better understand our discuss lectures with a few solved problems. So the first question is: structural cracks basically result from a incorrect design, two, foundation settlement, C, B, foundation settlement, C, faulty construction practices, or D, all of the above. Okay, so what is true? So if we remember, structural cracks result from incorrect design, overloading, foundation settlement, faulty construction practices, and earthquake. Okay, etc. So if we see here, incorrect design is correct. Okay, then foundation settlement is also correct, and faulty construction practices is also correct. So all of them are correct. So D, all of the above is the correct option. Second question, choose the correct option regarding active and dormant cracks. A, cracks due to thermal expansion are dormant cracks. B, cracks due to freeze thawing are active cracks. C, shrinkage cracks are active cracks. D, all of the above. So if you remember, the thermal expansion cracks, okay, so they are basically active cracks. It happens regularly. Similar is the case with freeze thawing cracks, okay, they are also active. But shrinkage cracks, they are, after it the process occurs, it is dormant, okay, it does not happen. So that is a this one, it is a basically it is one time event, okay, so but the others are multiple repetitive events. So basically these are dormant cracks, okay. So A is not correct, B is correct, and C is also not correct, okay. So B is the correct option. So that is written here. Cracks due to thermal expansion are active cracks. Cracks due to freeze thawing are active, and shrinkage cracks are dormant cracks, okay. So therefore B, cracks due to freezing thawing are active cracks, is the correct option. Third question. Pull-out test is a type of A, non-destructive test, B, semi-destructive test, C, destructive test, or D, none of the above. Sorry. So if you remember, pull-out test is basically a semi-destructive test. Okay. So that is written here. So B, semi-destructive test is the right option because we are partially damaging the top surface. Okay. 4. Pull test is a type of A. Pull-out test, B, penetration resistance test, C, pull-off test, or D, all of the above. So if you remember, the pull-out test had basically two types. Okay, one was lock test. Okay, lock means men punch in this one. I'm sorry. So there was lock test, which meant punch in Danish, and one was capo test. So that was in capo test, the basically the equipment that didn't need that needn't the equipment was not necessary to be placed before casting, so it was post cast. Okay, but in lock it was precast. So this is a type of pull out test. Okay, so as you can see here, so here this it without the need of pre-install insert. So that was insert I was talking about. So the equipment or the insert was it could be post installed. Okay, so that's a that was what the capo test is all about. So it is an example of pull out test. So it is the correct option. Fifth question. Powder actuated gun is used in A, probe penetration test, B, pin penetration test, C, pull off test, or D, all of the above. So if you remember this powder actuated gun, so it is used in the probe penetration test. Okay, so it was using penetration resistance test, which had two types. One was pin penetration, one was probe penetration. So powder actuated gun was used in probe penetration. Okay? So if you remember this figure, probe penetration testing on concrete. So it is the correct option. Sixth question. After doing core test, compressive strength of the core is found out using compression testing machine. Equivalent cube compressive strength of the concrete is equal to, as per Indian standard, A, cylindrical compressive strength, B, 5 by 4 times cylinder compressive strength, C, 4 by 5 times cylinder compressive strength, or D, 1 by 2 times cylinder compressive strength. So if you remember, for finding the equivalent compressive strength of concrete, we needed to multiply by 1.25. That was 5 by 4, okay, of the cylinder compressive strength. So that's the so that is B basically. So B, 5 by 4 times cylinder compressive strength is the correct option. So here also it is written. So therefore B, 5 by 4 times cylinder compressive strength is the right option. Seventh question. Statement 1. Characteristic compressive strength of concrete will be more if the rebound hammer test is conducted keeping the plunger in upward direction. Statement 2. In case of rebound hammer test, harder surface gives higher rebound. A statement 1 is correct, B statement 2 is correct, C both are correct, or D none are correct. So it is second statement is true, that harder surface gives higher rebound. Okay, so therefore 2 is correct. But if you remember this characteristic of compressive strength, basically, so if we remember that the maximum strength had occurred when the plunger was when the plunger was vertically downward. Okay, so that means that gave the maximum. Okay, and the minimum was when it was vertically upward. Okay, and horizontally it was in between. So here it is less, not more. Okay, so 1 is not correct, so only 2 is correct. Okay, so B statement 2 is correct, is the right option. So if you see here, this is lower. Okay, not high. Okay, so this is the wrong. Okay, so only 2 is correct, so B is the correct option. So B statement 2 is correct, is the right option. Eighth question. In case of UPV test, a higher pulse velocity shows concrete quality is good. B. Indirect or surface probing is more efficient than cross probing. C. Once the ultrasonic pulse impinges on the surface of material, the maximum energy is propagated parallelly along this face of transmitting transducer. D. All of the above. So, if you remember, the higher pulse velocity shows concrete quality is good. So, that is correct. A is correct. B. Indirect or surface probing is more efficient than cross probing. No, it is less efficient. So, B is not correct. C. Once the ultrasonic pulse impinges on the surface of material, the maximum energy is propagated parallelly along the phase of transmitting transducer. It is wrong. It is minimum. Okay, it is as much as I remember, 2 to 3% energy. Okay, so it is less energy, minimum energy. So C is also incorrect. So D is also cannot be correct. So A is the right option. Higher pulse velocity shows concrete quality is good. So here it is written, once the ultrasonic pulse impinges on the surface of material, the maximum energy is propagated at right angles to the face of transmitting transducer. Thus, best results are obtained for direct transmission or cross probing. Semi-direct and indirect or surface probing not as efficient as cross probing. So A is the correct option, as you can see. Ninth question. In case of half cell uh, uh, potential measurement test, A. Half cell potentials of steel in concrete can be measured directly at the concrete steel or steel interface. B. The potential at any point can be measured relative to a reference half cell placed on the concrete surface, which functions as an electrolyte. C. The negative terminal of the voltmeter is attached to the reinforcement and the positive terminal is attached to the half cell. D. All of the above. So if you remember, half cell potentials of steel in concrete can be measured directly at the concrete steel interface. So this is not correct, okay? Because this is the drawback, if you remember. So half cell potential of steel, it can be like for that we have to remove the cover basically, okay? So in the steel interface is true, but concrete interface is not true. So A is incorrect. We have to remove the cover. So B, potential at any point can be measured relative to a reference half cell placed on the concrete surface, which functions as an electrolyte. So this is true. Okay, so one is the if we can remove the cover, so we can take the rebar as the positive terminal, and the half cell can be placed at the surface, and it can be considered as the negative terminal. Okay, so that is that. So that exactly is the opposite of what is written in C. So negative terminal of the voltmeter is attached to the half cell, not reinforcement, and the positive terminal is attached to the reinforcement, not half cell. Okay, so C is incorrect, and therefore D is also not correct. So B is the correct option. So here it is written, half cell potentials of steel in concrete cannot be measured directly at the concrete steel interface due to the presence of concrete cover. Okay, so that is what I told. The potential at any point can be measured relative to a reference half cell placed on the concrete surface, which functions as an electrolyte. The positive terminal of the voltmeter is attached to the reinforcement, and the negative terminal is attached to the half cell, which is written opposite. Okay, which is opposite in the option. Okay, so B is the correct option. So as you can see, B is the correct option. 10th question. Statement 1. X-ray diffractometry is used to identify the crystal phases present in a material. Statement 2, scanning electron microscopy is only used to analyze non-crystalline materials. So which is correct? A1 is correct, B2 is correct, C both are correct, or D none are correct. So this is true. Okay, XRD is used to identify crystalline phases. So that is present in a material. That is mainly because in case of amorphous materials, because they are not orderly arranged. Okay, so they are unordered arranged. So there is a hump generated in XRD. That is mainly because XRD, because of the X-ray. Okay, so it is a very high energy. Okay, energy ray. Okay, so that energy of the ray is not being able to be absorbed by the amorphous phases, because it is because of its unorderly arrangement, it is weak. Okay, so it is not able to take that. Okay, so that's why that phase is not developed. Okay, intensity is not developed. But crystalline phases, because of their orderly arrangement, so they are very much strength, they have high strength. Okay, so the crystals are high strength, so that's the reason why they can take the energy intensity, and that's why they give big and very very crisp peaks. Okay, very high intensity peaks, and with less width. Okay, so that is true. Okay, one is true. The statement 2, scanning electron microscopy is only used to analyze non-crystalline materials. So that is SAM is used for both crystalline as well as non-crystalline, not only for non-crystalline. So 2 is incorrect. Okay, so 1 is correct and 2 is incorrect. So therefore 1 is A is correct. A statement 1 is correct. Here it is written, statement 1, X-ray diffractometry is used to identify the crystal phases present in a material. And statement 2, scanning electron microscopy is used to analyze both crystalline and non-crystalline materials. So that is the difference. So A is the correct option. So as you can see, A statement 1 is the correct option. With this, we will end today's discussion. So let us meet next class, next Sunday, and we will carry forward with our discussion for the third week course contents. Okay, so with this I would like to end today's discussion. Thank you.